Hello, scholars, and welcome to Mr. Chambers Teaches HMH Into Math for 5th grade. Today we will be working on Module 2, Lesson 2. These are pages 37 through 42 in your Unit 1, Module 1 through 9 workbook. In this video, we will go through the Module 2, Lesson 2 with the Spark Your Learning, Build Understanding questions, and a few select questions from Check for Understanding and On Your Own. Feel free to skip around in the video to find help working on the particular problems you may need help on. Today, in Lesson 2, we will be representing division with two-digit divisors. Our objective, or our I can statement, is I can find the quotient of numbers up to 4 digits divided by two-digit divisors using visual models. Spark our learning. We are a game designer, designing a treasure hunt game similar to the one shown. The game board is a grid with a treasure chest located behind one of the squares. The rectangular grid will have 96 squares. If the length of the grid is greater than 10 squares, how wide can the grid be? Here we know that our total number of squares will be 96. However, our divisor is also unknown to us. We know that it has to be greater than 10 squares. So this means that it could be 11, 12, 13, 14, and so forth. My thinking with this is I'll start with the lowest number, write out the multiples, and see which one can get me to 96 the fastest. So if I do my multiples of 11, I have 11, 22, 33, 44, 55, 66, 77, 88, and 99. 99 is too big to divide evenly, so it cannot be 11. Now on to my 12s. I know that my multiples of 12 are 12, 24, 36, 48, 60, 72, 84, 96. Hey, that's the number we're looking for. So our rectangle is going to be 12 wide, and I know that 96 is the first, second, third, fourth, fifth, sixth, seventh, eighth multiple of 12. So our grid will be 12 by 8, because 12 times 8 equals 96. The game board can be 8 squares wide. Build for understanding. Number 1. We're designing another game in which the players need to arrange flower pots into 12 equal-sized groups. There are 156 total flower pots. How many flower pots are in each group? As a multiplication table, we know that we have 12 times an unknown number equals 156 flower pots. As a division, we have 156 divided by 12 equals P. I forgot to read that last sentence there, where instead of having a box represent our unknown, we're having the letter P represent our flower pots. So 156 divided by 12 will equal P. Let's think about how we can break up pieces of 156 to add up to the multiples of 12. Along my side, I can write out my multiples of 12, 12, 24, 36, 48, 60, 72, 84, 96, 108, and 120. Looking at this list, I see that 120 and 36 would add up to equal 156. 120 I like because that is 10 times 12, and 36 is 3. These partial quotients mean that I can have 13 rows for our flower pots, or 13 groups for our flower pots, I should say. Over here, In this grid, I can count out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Each row has 13 in it. If I count out 12 columns, my 12th column would have 156 total flower pots, meaning we can ignore the last two here and have 156 total here. So in our array model, where we go 13, 26, 39, and so forth till we get to 156, our rows represent our divisor and total squares are dividend. The dividend in our array model here is the total number of squares. Our dividend is always our total, the largest number that we have. Our quotient is represented by the unknown left-hand side. The quotient is the unknown width of the square. Following our math earlier, in our partial area model or in our array model, we know that we have 13 groups of 12 to equal 156. So there are 13 flower pots in each group. On to build for understanding, number 2. There are 675 gold bars hidden throughout the game. The same number of bars are placed in each of 25 treasure chests. How many bars are in each treasure chest? First off, what division equation models the situation? We have 675, that is our total or our dividend. And we know one of the factors that will multiply to equal 675 is 25, so that is our divisor. Now we're going to use this area here to break it up into multiples of 25. And for our multiples of 25, it's nice and easy. It's 25, 50, 75, 100, 125, 150, 175, 200, 225, 250, and so forth. To help us out with this, I like 250 as a multiple because 250 is a multiple of 10. And in math, anytime that we can make it a 10, it makes life so much easier. If I have two 1050s or 250s, that equals 500 total, leaving me with just a difference of 175, which is the first, second, third, fourth, fifth, sixth, seventh multiple of 25. If I add up these partial quotients, I get 27 gold bricks in each of our treasure chests. These smaller rectangles in this term represent our partial quotients. The smaller rectangles represent are partial quotients. Based off the math that we showed here, there are 27 gold bars in each chest. All right, our last build for understanding question. Archaeologists find a sunken chest of 3,420 bronze coins. If the coins are to be shared equally amongst 20 museums, how many coins does each museum get? How can we model this using a division equation? Well, we use our total, 3,420, as our dividend. We put it under our division bracket, and we are now using our other known number as our divisor. So it will be 3,420 divided by 20. Now we can draw an area model to find the quotient. With this area model, I'm going to break it up into 3 easy parts. 3,000, 420, because all of these will be multiples of 20. Starting off with the easiest, how many times can 20 go into 20? That's 1 times 20 times 1 equals 20. How many times can 20 go into 400? If I remove the last zero, it's how many times can 2 go into 40? That is 20 times. Now, in my 3,000s, if I remove my last zero, it's how many times can we split 300 divided by 2, or what is half of 300, which is 150. If I add these all up, I get a total of 171. Each museum gets 171 coins. This was relatively easy, knowing that all of these numbers were divisible by 20 evenly. As proof of concept, if I were to divide this using our division equation, if I take off the last zero, 2 can go into 3 1 time, minus 2, carry down the 4. 2 can go into 14 7 times, minus 14, carry down by 2, and 2 can go into 2 1 time. Regardless of how I do it, whether I'm using an area model or standard division, I get that each museum gets 171 coins. Now on to our check for understanding. We'll do this on the next page for problem number 1. There are 76 bottles of paint in the art studio. The art teacher divides them equally among all 19 students in class. How many bottles does each student receive? To help us out, we can write this as a division problem. 76 divided by 19. Well, I know that there are 19 students, so I need to list out my multiples of 19. This one's a little bit trickier because this isn't on our multiplication table, so we have to think about it. But what's 19 plus 19? 38. Plus another 19 would bring us up to 57. And one more 19 adds up to 76. 76 is the fourth multiple of 19. By writing it out, I can figure out that 19 times 4 equals 76 and can subtract from there. Next up, we will do problems 3 and 5 found on page 41. Problem number 3. Write a division equation that is related to the application of distributive property shown. 12 times 100 plus 20 plus 4 equals 12 times 100, 12 times 20, 12 times 4. If we multiply these all out, we have 1,200, 240, and 48 and they all add up together to equal 1,488. Now, as a division equation, we're going to take our total number here, 1,488. That will be our dividend, the number that goes underneath our division bracket. Our multiple that we are multiplying by is going to be 12. And so that becomes our divisor. We are dividing 1,488 divided by 12. This will give us a quotient of 124. To show out the math of how this division equation looks, we know that 12 can go into 14 one time. 14 minus 12 leaves us with a product of, or leaves us with 2. If we carry down the 8, 12 can go into 28 2 times. 2 times 12 is 24, which brings us down to 4. Carry down our 8. 12 can go into 48 4 times, minus 48, for a quotient of 124. Next up, question number 5. Multiplication of two numbers results in partial products 210, 210, and 3. One of the factors is 30. Write a multiplication and division equation to model this situation. So if one of our factors is 30, we have 30 times blank equals, and I can add up these numbers up here. Our partial quotients get our total quotient of 213. Okay, so now we need to figure out what times 30 gives us a partial product, or gives us a product of 213. So as a multiplication problem, we have 30 times blank equals 213, and 213 divided by 30 will equal the unknown number. It's not asking for us to solve the equation, just to figure out what our multiplication and division problems would look like. Now, for this situation, these aren't going to give us even numbers, because 30 can't evenly go into 213. 30 can, if I write out our multiples, and I can figure out the closest I can get to 213, which would be 210, which is the 7th multiple of 30, but this would leave me with a remainder of 3. All right, on to our final 3 problems for today. We're going to be doing problems 7, 9, and 11. Here, we can use either standard division or an area model to represent 925 divided by 25. I can write on the side my multiples of 25, which we've already done once in this lesson, thinking about what numbers can add up to give us 925. Well, if I carry my thinking down here, I know that a multiple of 25 is 300. 300 happens to be the 1st, 2nd, 3rd, 4th, 5th, 6th, 175, 200, 8th, 9th, 10th, 11th, 12th multiple. And I know that 3/300 equals 900 plus 125 means that I have 12 plus 12 plus 12, 36 plus 1 37. Based off my area model and my partial number, or my partial quotients, I know that 25 can go into 925 37 times. But I also want to show proof of concept how this works. So in my division equation, 25 can't go into 9, but into 92 it can go in 3 times. 3 times 25 is 75. Subtract this out with some regrouping. 12 minus 5 gives me 7. 8 minus 7 is 7. So now I'm at 17. Carry down my 5. How many times can 25 go into 175? Well, if I have my multiples of 25, then I write out over on the side. I count that it is the first, second, third, fourth, fifth, sixth, seventh multiple of 25. So, whether I'm doing the area model or the division model, I know that my math shows me that it is 37 is our answer. All right, moving on now. We are going to do 54 into 1,134. List out my multiples of 54. 54 times 2 be 108. Plus another 54, 172. Plus 54, finding my patterns here. Four plus 2 is 6. 5 plus 7 is 12. 226 plus 54 will give me 4 plus 6 is 0. 5 plus 2 plus 1 is 8. 280 plus 54. Writing out my multiples. It may take a while, but this is a quick way of going about this. Plus 54, 4, 13, plus 1, 334, plus another 54, be 8. 8, 388, so forth. Maybe I'll find another multiple. I'm seeing pieces with how 54 can go into 1134. Keep adding this all up. 4 plus 8 is 12. 5 plus 8 is 13, 14, 442. Let's do a few more multiples. 6, 9, 496, and 540. All right. So, of my first 10 multiples here, trying to think of what would best add up to 134. Well, I like that 334 ends with the 34 that we need. And if I subtract 1134 minus 334, 0, 0, 11 minus 3 is 800. Now, to add up to 800, if I do 540, $260. All right, I can't divide this evenly. 1134 divided by 54, but I know, based on my partial here, 334 was the 1, 2, 3, 4, 5, 6th multiple. 540 was the 10, so I'm at 16 as my partial quotient, and closest I can get to 260 is 226, which is the fourth. So it's going to be approximately 20. Now, proof of concept. What happens when we actually divide out 1134 divided by 54? My comment's in the wrong place. My apologies. All right, 54. The closest multiple of 54 that can go into 113 is 2 minus 108. 113 minus 108 leaves me with 54 and 21. Somewhere in here, I made a mistake because I had 20 with a remainder, but I probably made my mistake somewhere around here to find my multiples, and that's okay. Sometimes in math we make mistakes, and that's why we try different possibilities to study and learn how the math works. All right, last problem for today's lesson. Number 11. The area at the bottom of the pool is 1,250 square meters. So if I imagine my pool, the bottom of the pool is 1,250 square meters. The pool is 50 meters long. I need to write a division equation to solve this problem. So my total is 1,250. That's my dividend. I'm dividing by my known divisor of 50. I can write out my multiples of 50, 50, 100, 150, 200, 250, 300. Just practicing my skip counting, counting on up, and writing out all the multiples that I know. I see that I have a 500. If I were to do my area model, I know that 500 is 50 times 10. 500 is 50 times 10. And that leaves me with a total of 1,000, which means that I only have to go to 250, the fifth multiple. 250, which is 5. Following my area model, my partial quotients, I add all up, will give me a total quotient of 25. To help us out, proof of concept, we are going to divide 1,250 divided by 50 to show that the division equals what our model shows. All right, because I have placeholder zeros, I'm really just measuring how many times can 5 go into 125. So I take off my placeholder zeros. 5 can't go into 1, but 5 can go into 12 2 times. Minus 10 leaves me with 25. 5 can go into 25 5 times, and regardless of how I did this, whether I'm doing standard division or I'm looking at my area model and breaking it down into multiples of my divisor, my answer is 25. So it is 25 meters wide. This now concludes our video on HMH Into Math for 5th grade. I'm Mr. Chambers, and I thank you for taking the time to watch this video to improve your math skills. And I look forward to speaking to you again in our next lesson, Module 2, Lesson 3.